Welcome to the module on economic aspects of battery recycling and second life. This section focuses on the economic value of battery recycling and second life applications. Recycling can recover metals like lithium, cobalt, nickel, and lead, reducing dependence on mining and exposure to volatile raw material prices. Second life use extends battery value by deploying packs in less demanding applications such as stationary storage, peak shaving, and backup power. Global demand for batteries continues to grow across consumer electronics, electric mobility, and grid storage, which in turn increases demand for critical materials and the volume of batteries reaching end of life. Whether recycling technologies can scale successfully depends largely on their economic performance. Profitable systems attract private investment and industrial expansion, while unprofitable ones often lead to operational losses or informal recycling practices. Finally, second life applications only deliver real value when the costs of testing, certification, and liability management remain under control. In the linear system, materials are mined, manufactured into products, used, and then disposed of, leading to high resource consumption and waste. In a circular value chain, batteries are first collected after use, then reused or repurposed in second life applications, and finally recycled to recover valuable materials for new products. This approach keeps materials in circulation for longer, reduces dependence on virgin mining, lowers overall system costs, and minimizes environmental impacts. The preferred strategy is therefore to reuse batteries whenever feasible and recycle them at the end of their usable life. Revenue primarily comes from selling the recovered materials back into the supply chain. For lithium-ion batteries, the main value drivers are lithium, cobalt, nickel, and manganese, along with copper and aluminum from current collectors and graphite from the black mass. For nickel-based batteries, such as nickel metal hybrid and nickel cadmium, most of the revenue comes from nickel, and in the case of nickel metal hybrid, sometimes rare earth elements. However, regulatory requirements and compliant handling, especially for cadmium, can significantly increase processing costs. In lead-acid batteries, the business case is dominated by recovered lead, which can be reused directly in new batteries. Additional revenue is obtained from plastics and other byproducts. Overall profitability depends on high recovery rates, high material purity, and favorable commodity prices. Establishing stable offtake agreements with material buyers is critical for reducing price volatility and ensuring long-term financial stability. Battery recycling begins with collection and take-back, which involves coordinating with consumers and industrial partners and can represent a significant logistical expense. Transportation and storage add further costs, especially because spent batteries are classified as hazardous goods and must meet strict safety requirements. Once delivered, batteries must be sorted and identified by chemistry and format, which is labor-intensive and technically challenging due to mixed battery streams. Quality control and certification are required to ensure traceability and that recovered materials meet purity specifications. Disassembly and pre-treatment follow, involving both manual and automated operations, as well as safe discharge and handling to mitigate fire and explosion risks. The core processing stage is also capital and energy intensive, requiring specialized equipment, reagents, and continuous maintenance. Finally, waste treatment and emissions control generate additional costs through the management of wastewater, slag, residues, off-gases, and the operation of dust filters, scrubbers, and monitoring systems. Together, these elements determine the overall economics of recycling facilities and highlight why efficiency, automation, and scale are critical to achieving profitability. For lithium-ion batteries, the economic potential is high because of the valuable metals such as lithium, cobalt, and nickel. However, profitability is strongly affected by the mix of battery chemistries and volatile metal prices. In addition, processing lithium-ion batteries is technically complex, and safety and treatment costs remain significant. Lead-acid batteries represent the most mature and standardized recycling market. They achieve very high recovery rates, which supports a strong closed-loop business model. Because recovered lead can be directly reused in new batteries, the industry benefits from relatively stable and predictable profitability in many regions. Nickel-based batteries, including nickel cadmium and nickel metal hybrid, provide moderate economic value, mainly from nickel recovery. However, the volumes are lower and feedstock is less consistent than for lead-acid or lithium-ion batteries. Compliance and handling costs, particularly for cadmium-containing batteries, can be high, which limits overall profitability. High-value recycling goes beyond producing materials for new batteries. Instead, recovered battery materials can be upcycled into higher value products such as catalysts, adsorbents, and supercapacitor materials. This approach can significantly improve profit margins, particularly when metal prices are low and conventional battery-to-battery recycling becomes less attractive. However, success depends on achieving consistent material quality, scalable and reliable processing methods, and demonstrating real market demand for these advanced products. In addition, certification, product standards, and long-term buyer agreements are essential to ensure stable revenue and to make high-value recycling commercially viable. Second life applications are based on the fact that electric vehicle batteries are usually retired while they still retain a significant amount of usable capacity. Instead of recycling them immediately, this remaining capacity can be used in less demanding applications such as stationary energy storage. By reusing batteries, storage systems can be delivered at a lower upfront cost than new batteries. The economic value mainly comes from extending the asset life of the battery and postponing recycling expenses. However, the business case strongly depends on the costs of testing, repackaging, certification, and warranties. In addition, strict safety and performance standards must be met to ensure reliable operation and market acceptance. Second life batteries create value by serving applications that do not require the high performance demanded in electric vehicles. In renewable buffering, second life batteries store excess wind or solar energy and release it when generation drops. This increases self-consumption and minimizes energy losses. For peak shaving, they are charged during low demand periods and discharged during high demand hours, helping customers lower peak demand charges and avoid peak energy prices. In backup power applications, second life batteries provide fast and reliable electricity during outages, reducing downtime and improving resilience for critical facilities such as hospitals and data centers. Where market structures allow, second life batteries can also participate in grid services, such as frequency regulation and flexibility markets, creating additional revenue streams. Second life battery projects are driven primarily by operational and compliance costs rather than the battery hardware itself. Collection and logistics include the safe transport and storage of used electric vehicle batteries, which are classified as hazardous goods. Testing and grading are required to measure remaining capacity, internal resistance, and safety, ensuring only suitable batteries are reused. Diagnostics access is often restricted because battery data and software are proprietary, increasing evaluation costs. Disassembly and repackaging involve significant labor and specialized equipment, particularly when modules must be reconfigured. New battery management systems and control electronics are needed to ensure reliable monitoring and system integration. Thermal management systems and protective enclosures must be added to meet safety and regulatory requirements. Certification, warranty, and liability coverage create additional financial burdens related to risk management. Finally, operation, maintenance, and component replacement over the second life period must be accounted for in the total cost. Reuse or recycle. Batteries that retain sufficient capacity and show stable performance can be reused, enabling additional value creation at relatively low material cost. Reuse is only viable when the battery condition is well understood, diagnostics are available, and safety risks are manageable. If the battery is damaged, unsafe, highly degraded, or its quality cannot be reliably assessed, recycling becomes the preferred option. Recycling is also the final pathway after the second life period, allowing recovery of valuable materials such as lithium, nickel, cobalt, and copper. The overall objective is to maximize total battery value while avoiding increased safety, compliance, or liability risks. In summary, economics ultimately determines whether battery recycling and second life systems move beyond pilots. When the business case is strong, collection rates increase, investment follows, and industrial capacity expands. When margins are weak or risks are high, batteries are more likely to be stored, exported, or handled informally, reducing recovery and increasing environmental and safety concerns. Recycling profitability depends on the balance between material revenues and total processing costs. Revenues come from what can be recovered and sold at the required purity under existing market prices and offtake terms. Costs are driven by collection, logistics, safe handling and discharge, disassembly and pre-treatment, processing energy and reagents, and compliance, emissions and waste treatment. In addition, economic outcomes vary significantly by chemistry. Lead acid is the benchmark due to standardization, high recyclability, and mature closed-loop infrastructure that supports relatively predictable returns. Lithium-ion offers high long-term potential, but value depends on cathode chemistry and costs are higher due to pack complexity and safety measures. Nickel-based batteries typically deliver moderate value mainly through nickel recovery, while lower volumes and, for nickel-cadmium, strict compliance requirements shape profitability. Second life creates value through services rather than materials. Repurposed batteries can generate savings or revenues in applications such as renewable buffering, peak shaving, and backup power, but the business case depends on low-cost testing, grading, repackaging, and integration plus clear standards for safety, warranty, and liability. The strongest circular strategy is usually sequential. Reuse or repurpose when performance and risks are manageable, then recycle at end of life to recover materials and complete the loop. Thank you for your attention.